So much, Professor Griffith. And let me get started immediately. I usually like to have interactive sessions where I ask people to respond to my queries so that I know that people are engaged. And also it improves the transfer of knowledge or skills if it is done through active engagement rather than lecture and passive listening. So here is a quick outline of my talk. First, let me check, am I clearly audible, Professor Selvan?
Yes, Professor Karmalkar, yeah. Very clear, slides are also visible, yes, yeah.
So here is a brief outline of my talk. I will first talk about problem solving, and then I will describe what is engineering in a slide, and then I will consider in some detail example of an engineering problem and its solution. So, modern pedagogy says that to improve learning among our learners, we must specify not only the syllabus or the set of topics, but also what will be the outcome, what knowledge or skill will the learner get at the end of the session. So at the end of this talk, I'm assuming that, my audience are students because I usually give this talk to students, but doesn't matter, it could be anyone. Identify general thinking strategies involved in real life problem solving. Identify the need for interdisciplinary knowledge in real life problem solving. State the goal of and the knowledge and skills required for engineering. And finally, recognize the reason for subjects from diverse disciplines in the core engineering curriculum. For example, why does an electrical engineer undergo courses in chemistry, material science, economics, etc.? So I expect these to be the outcomes of my session. So I do not call it as a talk because, as I said, it is interactive. Let me quickly check if there are any students here.
Very doubtful, extremely doubtful, I think.
Okay, so even if there are, no students, I will assume that others will participate just as enthusiastically.
Yeah, sure.
Yeah. Okay. So now let me start with a few problems, and then identify what strategies were used to solve these problems, and then we'll make a list of these strategies. Okay. And see what are the barriers to solving problems. So that is the goal of this part of my session, first part. So let's take a problem like this. In fact, I picked this up from practical experience of so many years. Solve for x in the equation e power minus x equal to 0.5 plus x square. Now, what happened is, in some discussion with my research student many years ago, a problem like this arose, where I just said, ask the student to, why don't you just find out what is x, and then after you find out, then we will get back and discuss further things. And then I diverted myself to doing some office work which I had. Now I got engrossed in my office work, and I found it was more than half an hour, and I still didn't hear back from the student. So I asked him, so what happened? Why is it taking time? He said, actually, I was in a different location, right? And the student was in the laboratory. So he said, sir, the electricity has gone off. So the computer is not working. I said, but why do you need a computer? Sir, I usually use MATLAB and to solve problems like this. I said, that is fine, but why do you have to use only MATLAB for doing it? Why don't you just use a simple calculator and do it? Sir, my calculator is not programmable. So then I told him, well, let's do it, and it can be done within a couple of minutes. So here is what we did, right? So you just have a calculator, and for some reason your software is not working, which tries to do an iterative solution. So I said, let's put down like this. So what is basically an equation? Left hand side is e power minus x, right hand side is 0.5 plus x square. Now you have to find x such that left hand side is equal to right hand side. That is all what it is. So let's put some values. X is equal to 0. If I put, I get left hand side as 1, right hand side as 0.5. Now I find that left hand side is more than right hand side. I now change. Instead of 0, I now put 1 as x. Okay, randomly I'm putting. And then I find left hand side is 0.37, right hand side is 1.5. Now right hand side is more than left hand side. So I said, okay, the solution should lie between 0 and 1. So now let me try some number between 0 and 1. Let's say half of average of these two, right? 0.5. So now you find left hand side is 0.61, right hand side is 0.75. So now clearly the solution lies between 0 and 0.5, right? 0 and 0.5. So you take some value depending on how close these two numbers are. And then I try 0.4, I'm almost getting the solution. So that's it, it's over. You got x equal to 0.4. So what have we used? Basically, we have used strategies of trial and error and logical reasoning. Now, one can go through several problems that one faces, and one will find actually these two strategies are used very often, independent of the specific discipline in which the problem lies. Okay? But what happens is, usually we are stuck with some one approach of solving a problem, and we think that is the only approach. So we'll also summarize the barriers to problem solving from these examples. Let me take one more example. This is again some more than 2 decades ago. I got a call from my colleague who was in the chemistry department. I had just joined as a faculty then. And this other person also a young faculty. He said, Shreepad, can you just help me? You know, my computer is down and I don't know what's wrong with it. I said, but you know, why do you think I will have a solution for this? He said, no, see, you're an electrical engineer. And you know, electrical engineers are normally used to dealing with this kind of things. Appliances not, you know, working and so on, and they can quickly identify what is it. I said, look, I can come and help you, though I don't know whether you need an electrical engineer for solving this. Anyway, I went to his lab. I saw the computer was down. Okay, so I made a sketch of what was the arrangement. So here was the computer and it was connected with a wire to an uninterrupted power supply, and there was another wire. And then there is a plug, and this is going into the socket. Okay, so then what I did was, I said, okay, let me check. Out of these elements in this diagram, such as the computer, the wire, the UPS, and this wire, and the plug, and the socket here. In principle, any of these could have gone bad. The computer is down, but that doesn't necessarily mean the problem is with the computer. We don't know. So let's do a simple thing. So what I did was, first, I replaced this computer by another appliance, which was available in the lab. And I found that was also not working. So I said, clearly, the problem may not be with the computer. Definitely, there is a problem with the remaining part. Then I went on analyzing like that. I checked this wire, I checked the UPS, and I checked this wire plug. And ultimately, it turned out the problem was inside the plug. All that had happened was that the wire had come off. The wire which is tied up to these pins, okay, and screwed into that place, right, had come off. And that had happened because in those days, the entire setup was not very, there were not too many sockets to connect various appliances. So what would happen is people would connect into the socket one particular thing, let's say in this case, this UPS and so on, and use it. And then after some time, if you want to use something else and there is no another socket, so you remove this and then put the other appliance. So there were, these plugs were being removed and plugged into the socket too often. So because of that, the problem had occurred here. So I set it right. And then I said, that's it. So, there is nothing wrong with your computer. Okay. So now let's analyze. What is the thing here. So one issue is that this feeling that if you want to solve a problem, it requires a discipline-specific knowledge. The problem lies in a specific discipline. And so you need an expert from that discipline to solve it. So this is a mental set, okay, a barrier. And what did we use here really to solve problems? Again, if you see, well, first thing we did was representation or modeling. When you have a situation which is as a problem, you must put together all the elements that may be responsible for the problem. It requires certain amount of imagination, okay, but definitely a sketch of all those elements and how they're interrelated should be made. This is a very important first step. So this is what is called representation or modeling. After that, it's divide and conquer. For instance, now you separate the problem into parts. So is the computer down? Is the wire not working? Or is the UPS not working? Or is this wire not working? And so on. So part by part, you try to see. And then logically, the separation of the whole into parts happens logically, right? Using logical reasoning. So these three strategies you put together, and then that is what has helped you to solve this problem of why the computer is down. Now there is another word for this, and that is analysis. These three strategies together constitute what goes by the name analysis. So many times we see that students are used to certain terms without understanding what they mean. So what is analysis? It has three steps. Separation of the whole into parts. First, the problem is treated as a whole, which has several elements or parts. So you separate the parts, separate the whole into parts. So which is what we have done. Separate this whole thing into parts, that is computer, wire, UPS, and so on. Understanding the parts in isolation. And then you try to understand each part in isolation. Okay. And combining the understanding so obtained to understand the whole. And now this part by part understanding that you have got, that you should combine to understand the complete situation. This is what is analysis. So here, for instance, imagination is required here. How do you separate the whole into parts, right? So those who are in the area of semiconductor devices know this very well. You want to analyze a PN junction, a MOSFET, right? So every device, semiconductor device you want to analyze, you separate first into space, charge, and neutral region. That is one common separation for understanding any semiconductor device. And then there are further such divisions, right? So, and this applies to even other areas. So what we have done in effect is analysis. So an analytical ability is required to solve problems. It is not specific knowledge of electrical engineering that is required here. Really, that has been used. Okay, right. Let's take up one more. So usually what I do is when I'm conducting this session with my students, I pose the problem and I stop. For example, I will pose this problem, right? And then I'll give 5 minutes time to students. Okay, you try it. Let's see what is the approach. Even if you don't get the solution, let us know what is the approach, right? So I do the same thing with each problem, which I'm not doing here for a couple of reasons. Most of us are colleagues. So I don't want to, treat people as students. That is one thing. Second thing is there is a restriction on time. I usually conduct this over 1.5 hours, right? Okay. Now let me take one more problem. Just try. Let me try. Is there any student here? Any student? Can you please turn on your video? Any student who is here?
Maybe there are no students who would like to turn on their video.
Okay. No, then I will pick because I see some people who are my students.
Okay.
I see. Okay, let me randomly pick. So Savani, it doesn't matter if you are a student or not. Savani.
Someone has texted, are old students allowed?
Oh yes,
yes. Yes.
This is just just to have an engagement. That's all. So let me try. Savani was someone. Savani. I was just trying randomly first. Okay, if not, that's fine. Ashwin. Okay, fine. Ashwin, that's fine. You have turned on your. Yeah. So which place are you from, Ashwin? Unmute yourself.
I'm in Albuquerque right now.
Sorry, please repeat.
I'm in Albuquerque right now.
Oh,
Albuquerque.
Okay, good,
Yeah.
good. So can you please read this thing out for us, this particular problem?
Divide a square piece of paper into 5 equal squares using scissors only. Cut and join is allowed. No paper should be wasted, nor can a paper be pasted over another.
Okay, so now I will pause for a few seconds. Please read it very carefully. Okay, thank you, Ashwin. And then I will give everybody a little bit of time to think, how do you think we can solve this problem? Divide a square piece of paper into 5 equal squares. See, please remember these 3 words. You are dividing into 5 parts. Each of the parts should be a square shaped. Okay, and all the squares should be of same size. And only scissor is given. You can join, you can cut into any number of pieces and join if you want, but no paper should be wasted, nor can a paper be pasted over another. Okay, I'm giving you a few minutes. So I have a clock here. Okay, to get you initiated, let me discuss a variation of this problem, right? Supposing I change this number from 5 to 4. Let me, I just want to ensure that people understand. Supposing I change this number 5 to 4. Can someone tell me what would be the solution? Anyone? Jaipal, can you tell me what is the solution if I want to divide a square piece of paper into 4 equal squares?
It maybe we can divide it into 4 pieces. Yeah?
I know how. That is the question. Can you describe?
First of all, I have to fold the papers into, I actually double the paper and I have to again double the paper. By using scissor, I have to cut the paper.
Sorry. So now just pause. I will give a few seconds time. Just think and then, so that you can compose your sentences. And then this is, so now what we are talking about is communication. Another thing engineers need is communication skill. How do you communicate your ideas, right? So please think for a few seconds and then tell me the solution for this. And then we'll move back to the previous problem.
Yes, sir. First of all, I have to measure the paper. Then by using scale and pencil,
so now,
I have to.
1 minute. So this is where there is a reason why I'm discussing the problem, so that we must be sure that we have understood what is the problem. You have no way of measuring because you are given only scissors. Please note this. Scissors only have been given.
Yes, sir. By looking the shape of the paper, we can decide that it is in a square shape.
Sorry, can you please repeat?
By seeing the size of the paper, I can decide that the paper is in the form of a square.
Yeah, let us say you have been given a square piece of paper. It is a square. Yeah.
Yes, we know about that for a square, all the sides are same.
Correct.
Then I have to fold the papers.
Okay. So you tell me, where will you fold?
By upper side or other side. It's not a big problem. From upper to bottom, lower to bottom, or from right to left. It's not a big problem.
So I'm sure you know what is the solution. I am just trying to point out what is required for engineers, just
Yes, sir.
as a slight byproduct. Sorry,
Yes,
as
sir.
a minor distraction it might look, though we are discussing engineering problem solving, all engineers should have communication skill. So can you try to make it a little clearer? You are right that you have to fold the paper and all. So how will you express it? Anyone else would like to try this? I'm sure you have the solution, but you also need to learn to express. I'm trying to point out what are the skills required for engineer. Okay. Anyone else quickly, can you tell me what is the solution to this? Just turn on your mic and tell.
Can I maybe answer
Sure,
if just like
sure,
fold
sure,
it,
sure.
fold it in the middle. So we'll
Yeah.
take like the top part and like fold it so that it's aligned at the bottom. And then
Right.
we will do the same thing. We will fold the paper from the left to the right, and then we're gonna have that trace, and then we just cut along the trace. I
Right.
believe it's like
So-
that. Yeah, kind of like that.
Correct. So that is what. So this is what it is. So you fold the paper as he just now said that you align the top edge with the bottom edge. You fold it so that the top edge is aligned with the bottom edge. That means the fold will occur here. And then you similarly fold so that the right edge is aligned to the left edge. Then the fold will occur here. Now you cut along these two lines. So you have only used a scissor and then you have four pieces. Now we go back to this problem. I'll now give you, so now what we are looking for, I'm sure all of you know. I will again give you a few minutes time. Okay, please think about it and tell me, what is the strategy for solving this problem?
Can I attempt?
Oh, sure, sure.
Maybe we can.
Can you kindly introduce yourself? Just one sentence about yourself.
Okay. I'm a faculty at SSN University, SSN College of Engineering itself.
Okay.
So
Which area, which discipline?
I'm in mechanical engineering.
Okay, good. Yeah.
Okay. So
So
maybe
first,
we
let me
can
ask you, have you
Okay.
attempted this problem earlier?
No, I haven't. I've
Okay.
kind of just been trying on my book right now.
Good. No, that is important because if you attempted earlier, of course, then the discussion is not, it won't be that enlightening. Yeah, please go ahead.
Right. So the very first approach that I had was to divide it into 5 equal parts and then, cut into 5 equal rectangles, I was thinking.
Okay. So you are saying you will cut something like this one, two,
Yeah,
like
but then I figured it's not going to be easy to rearrange their areas into a square.
That is point number one. Point number two, how will you know 5 equal parts? How will you make?
Okay, so
Because
that's
you are
also
given
another
only a
question.
scissor. You are given only a scissor.
Right. So I was actually thinking maybe we can divide it into 20 parts that way. 20 parts. So rather than not 20 parts.
Can you tell me? Tell me 20. How do you do it?
So we first divided into 4 parts, and then
4 parts the way we did. You mean like this one?
Right.
Okay.
And then again divided into some more parts. So not
True.
20, but maybe we'll have to do into 16 parts or something like that. Each
so
one.
You mean, okay, further divide each of these small squares like this.
Right.
Okay.
And then see where we'll reach the least common multiple.
Okay, so you are saying, let's say I have 16 parts and I need 5 equal squares ultimately.
Right. So I actually thought, okay. Okay. Now I actually thought I can divide it into 25 equal squares, but okay, that's a good point. Okay, let me just think about it
Sure,
once
sure,
again.
please.
Sure.
It
Yes,
takes
sir.
time. It takes time. In fact, this is a kind of discussion that is important. More than the solution, what we are discussing now will be important when I point out some things here in problem
Okay.
solving strategies. Yeah.
Sure.
Thank you so much, Anirudh. Thank you so much. Anyone else would like to give a try? You want some time, you take, right? The struggle is important. If you want to learn problem solving, the struggle is important. So I'll take just one more response and then I will proceed further to discuss what we gather from this exercise. Another person would like to suggest how we could go about solving this problem? You need not give the ultimate solution. You can suggest an approach. So one approach that Anirudh was trying is you divide vertically and horizontally, right? That was the basic strategy. You try one number of parts and maybe more number of parts, but the strategy is divide vertically and horizontally. Anyone would like to it doesn't matter if your solution is not correct, right? It's not important to be correct here. It is about the strategies that we have to use for solving problems. Mohit, Saili, Mohit.
How about I will try again? I think it's a bit difficult question because
you are the host, so you will,
yeah, I'll just have to answer, all these questions. I mean, if we just can only fold the paper and cut, right? And I was just like wasn't sure if we need like only 5 squares out of like the whole piece, or we can have many and there will be 5. So I'm just like wasn't clear about the description of the problem, but what I will probably do if we just first fold it the way that we did for 4 squares, and then like once we have like
whatever we did
like
here.
that, and then if like what we can do if we need to like cut more squares and like what we can do, like we will take like the top part and like fold it against the center line. And then we're gonna get line between the top line and like the one in the center, and then we can do like same thing with the bottom, and then we can do the same thing with the left and with the right. So we'll take the left side of the paper and gently fold it so that the left part of the paper will be aligned with the center line, like a vertical center line. So if we do top and we do left and right, so we're going to have like another set of squares in each of these big 4 squares that we have, and then we just cut. But then we will have more than 5. Right. So, and well, I just wasn't sure if we're allowed to have more than 5. So if 5 is maximum or not.
Yeah. So that is why this statement is given.
Yeah, so that's why maybe
yeah.
it's not like that like easier to answer this question. That's why probably like nobody can answer.
So yeah, so thank you for that. So now I will just this is not a simple problem. Let me just tell you in advance, right?
Yeah, it looks like it's not that simple.
Yeah, it's not a simple problem, and you can attempt it. I will not give you the solution, so that those who want to try it out, I will not deny them the pleasure of solving it. But let me just tell you some some ideas, because otherwise, because we have to summarize some strategies for solving the problem. So the point is, supposing I turn the problem and reformulate it. So instead of saying divide this square into 5 equal squares, I will say, can I join 5 equal squares and make a big square? Suppose, okay, I reframe the problem like this. Then what does it tell me? Let's assume that the side of each of these equal squares is 1 unit. So the area of each square is 1 unit. Therefore, the area of the bigger square will have to be 5 units. This means each side of the square, bigger square, will be root 5 units. So now I have reduced the problem to realizing a root 5, a length of root 5, starting from a length of 1 unit. Can I put together several 1 units in some way to get a length of root 5? Right? So now the approach I am suggesting, it need not be the only approach. I'm just suggesting an approach. Okay. So now question is, how do I get root 5? So supposing I join 2 squares like this and see this particular side, hypotenuse of this right angle triangle, then this is 1 unit, this is 1 unit, this is 1 unit. So 2 units, 1 unit. So this is root 5. Similarly, this is root 5. So that is how I'm able to get root 5 out of these squares. Now I will not solve the problem further, right? You can try it yourself. So let us summarize what strategy was used in this particular approach that I was suggesting. So reformulation, you restate the problem. You are given a starting point and you are given an end point. Instead of that, try to see whether the end point can be made as a starting point and the starting point can be the end point. Okay, that is one method of reformulation. This is not the only method, but essentially it is reformulation. So this is one thing that one can attempt to solve problems. And second is reduction. So you reduce the problem to another problem, which may be of a lesser complexity, which may appear to be of a lesser complexity, and you solve that. So these are the 2 strategies we have used. Fine. Now let me summarize from these 3 problems that we attempted. What are the strategies? So the strategies we used were trial and error, logical reasoning, representation or modeling, divide and conquer, reformulation, reduction. And there is one thing I didn't discuss, but which is very, very important, and that is by use of analogy, solving problems by use of analogy. So this is a very, very important area, right? In fact, research in psychology on inventions and innovations have shown that almost all innovations have been made through analogical thinking, analogy, right? What is it? Incidentally, before I do that, the combination of this is called analysis, as we said. So the analogy is nothing but transfer of existing ideas to new surroundings. Transfer of existing ideas to new surroundings. Let me quickly give you a major solution, right, that we all know of, which was achieved by analogy. There are many, all other solutions also can be shown to have emerged by analogical thinking, but we don't have time to go into that. So the example I would like to cite here is that of the atomic structure. So how did the scientists come up with the model that every atom contains a central entity like the nucleus and another entity like the electron revolving around the nucleus? So this model was motivated by the observation in the macro world, M-A-C-R-O, macro. The macro world, so people over thousands of years had seen that you have, for example, the planetary system. You have the sun and you have the planets revolving around it. Okay. So if the macro world is arranged in this fashion, couldn't it be that micro world is also arranged in the same way? So this was the starting point of the thinking of the atomic structure. And looking at the structure as a possible central entity which is fixed, and then other things revolving around it. Okay, so there are many other examples that one can give, but so these are essentially the problem solving strategies. Now let us also summarize what are the barriers to problem solving. What did we find as the barriers? For example, when I'm trying to divide a square piece of paper into 5 equal squares, I am trying to use vertical and horizontal cut. Okay, so this is an example of a barrier, because it is not necessary that every problem of paper cutting should be solved by making cuts parallel or perpendicular to the sides, right? But we started working with that approach first until we hit a dead end and we said, oh no, looks like this approach won't work. Okay, and functional fixedness. Okay, so what are these two barriers? Let us elaborate on them. Mental set is a mental bias to stick with only the solution approaches that have worked in the past and stubbornly ignore alternatives. This is one of the reasons why we are not able to solve problems. Mental bias to stick with only the solution approaches that have worked in the past. Okay, and stubbornly ignore alternatives. So this example of cutting the square piece of paper horizontally and vertically, okay, is an example that we cut into 4 pieces. We try variations of that number 5, and then we see, okay, 4 I cut vertically and horizontally, and then I get stuck to that approach. Okay, so this happens often to us, and the problem is that this is subconscious, right? So you have to tell yourself that, oh, maybe I'm getting stuck somewhere. What are the alternatives, right? And so on, consciously trying to explore alternatives. That is the only way this mental set can be removed. Another way it can be removed is actually you must have the habit of solving different types of problems, right? Rather than solving only one type of problems. So this is what is to be done to remove this particular barrier, mental set. Now, what is functional fixedness? A mental bias that blocks people's ability to use an object or concept for something other than what it is usually used for. Okay. So this thinking, for example, that if I want to identify why my computer may be down, I think I need electrical engineering, right? Knowledge of electrical engineering, knowledge of a particular discipline. So in fact, it's interesting. I want to cite one more example of this. My son, when he was in 7th standard, I told him that, before his annual exams, I told him that, I will check your preparation. So after you think you are prepared and rehearsed everything, the entire material that has been taught over the year, you come to me, I'll give you some problems, and then I will test whether you have done your job thoroughly. So I gave him a problem to work on. After struggling for a couple of minutes, he said, Father, which chapter is it coming from? I said, how does it matter? Okay, it could be from, you have studied 5 chapters over the year. It can be from any of the chapters. You can figure out. He struggled again for some time. Said, no, Father, you must tell me from which chapter it is. Then I will be able to solve it. So anyway, then I told him, okay, it's from chapter 3. As soon as I told him it is chapter 3, he solved the problem. So this is another problem, right? So we feel that we should be told the specific knowledge that should be used to solve the problem. Our mind is not navigating across different sets of knowledge that we have acquired. Naturally, it is not navigating across. We expect a hint for that. So this is an example of functional fixedness. So we need to avoid these barriers. Now, this is what essentially is involved in engineering problem solving. Now, in the remaining time, I would like to just discuss some practical engineering problems. So let me define engineering for all of us. Ultimate goal of engineering is products and processes aimed at practical ends. Again, students use these terms without understanding what they actually mean. So it is useful to define them. And that is why I feel talks like these are very important. Okay, which may not fall into the category of, which may not fall into any syllabus for any of the courses. Okay. So ultimate goal of engineering is products and processes aimed at practical ends. That's the goal. Now, these products should be safe, eco-friendly, efficient, economical, reliable, easy to fabricate, and so on. There are some qualities like that. Now, what do you require? What knowledge and skills are required for this? Knowledge, a reasonable knowledge of science, mathematics, logic, economics, ethics, etc. Now, grasp of nuances or details may not be necessary, but you need knowledge of a wide range of disciplines. This is important, though it may not be to very great depth. Another important ability is, or skill, is the identification of variables that can be ignored in a given situation based on hands-on experience and intuition. Ability to identify variables that can be ignored in a given situation based on hands-on experience and intuition. How to simplify this problem. Approximations. This is another very, very important ability an engineer should have. How should I approximate? And critical and creative thinking, what we have just discussed, all those strategies, they fall in this area of critical and creative thinking. And communication skills. How do you express your solution? Okay. So these are basically what is required for engineering. Okay. Now there are, you can classify engineering into 3 levels: software, systems, and components. Okay. Systems means building a supercomputer or, sending a satellite in space. So these are all building systems. Components. Components are those things which go into building a satellite or building a computer, like chips and so on. Now, this is the area in which I have been working. Semiconductor devices are nothing but components. Okay. So this area is highly interdisciplinary. So I will just describe in 10 minutes some problems which were associated, which came up when we wanted to develop, when we want to develop the technology of, technology of a tuning diode. A VHF tuning diode, very high frequency tuning diode. So let me give you what are the specs of this. It is a 30 to 300 megahertz, a device that is used in this range, and it's used for communication up to 100 kilometers in defense applications. Now, this is the structure of the device. So it contains a semiconductor chip, and there is a glass tube. I'm talking about the arrangement of this. There is a glass tube which is encapsulating this chip, and there are 2 leads which are made of metal, copper, for instance, or some alloy of copper. And there is a ceiling here, glass to metal ceiling. So these are the elements of this particular device. Now, while developing the technology, we encountered several problems as it happens. I will just talk about 2 or 3 things which can be talked about in the limited time to tell you how the same strategies that I have just discussed are required to solve the problem, and the barriers that I discussed prevent you from solving the situation, right? So I want to just focus on those same points here in this new context. Now, here is the further structure of this chip. So you have a P-type region semiconductor, an N-type semiconductor. Now, incidentally, the audience doesn't have to know about semiconductors and so on. Okay, I'm not expecting any such knowledge, deep knowledge of the area. And then it has some metal layers which are used as contact from the semiconductor to the outside world. So on this side, you have nickel, and on that you have a silver, and it is called a bump because it is thick. So this is basically the structure of the chip that you have to fabricate. These are the 2 leads, right? This lead here and this lead here. Okay. Now, what are the specifications of this? The breakdown voltage should be greater than 30 volts. the reverse current should be less than 10 nanoamperes at a reverse bias of 28 volts. And it is nothing but a variable capacitor, voltage variable capacitor. Its capacitance varies when you vary the voltage between the two terminals. And this variable capacitor is used to tune into different frequencies in the communication sector. The capacitance at 4-volt bias is 47 picofarads, and the quality factor measured at 50 megahertz should be more than 400. And these are the specifications. Okay, so now what is the meaning of this reverse bias? I have just shown a current voltage curve. In the reverse direction, the device breaks down at around 30 volts. That is the meaning. And what is the reverse current? This is the reverse current. 10 nanoamperes is the reverse current. Okay, at 28 volts. If you see 28 volts, that is how it will be. Okay. Fine. Now, let me talk a little bit about the capacitance and then tell you a problem that we encountered and how it was solved. So there is a voltage variable capacitor. So if you vary the voltage between the two terminals of the diode, the capacitance varies something like this. And this C4 is 47 picofarad, means that in 4-volt at 4-volt reverse bias, your capacitance will be 47. Now we encountered a problem related to Q measurement. So what is the Q quality factor? In fact, every electrical engineer should know, though may not be others. The quality factor is nothing but 1 by 2 pi into frequency at which the capacitance is being used into the series resistance associated with the capacitor. It's a parallel, it is a parasitic resistance, and C is the capacitance. So this quantity 1 by 2 pi FRSC is called quality factor. Why is it called quality factor? It can be shown to be equal to energy stored. All of us know that capacitance, even if we are not from electrical engineering, we know that capacitor essentially stores energy. But then not every capacitor is perfect. So some energy will be dissipated, right? Even though it is meant only for storing energy. So this ratio of energy stored to energy dissipated is called the quality factor. Now, what is the method of measuring quality factor? Basically, you have an instrument, okay, where you put your diode, which is like a capacitor, voltage variable capacitor, between two knobs, and then you put an inductor here. What should be the value of the inductance? The value of the inductance should be such that 1 divided by root LC. I'm sorry, there is a slight problem with the formula. I should put 2 pi here. Let me put that pi. Yeah, so right. So the inductance should be such that the 1 by 2 pi root LC should be equal to the 50 megahertz. And then this meter tells you what is the quality factor of the capacitor that you have put here. This is essentially the arrangement. Now, what happened is the place where we were developing the technology, they said that they don't have an inductor. The standard inductances are used, coils, to make this measurement. They don't have an inductor that will help us resonate at 50 megahertz, and said it will take a couple of months to get that. Now, so here what has happened is, you think that some standard things that are available are required to solve this particular problem of Q measurement. Now, it turned out that in fact, if you take a piece of wire, just a straight piece of wire of say 5 centimeter length, you calculate the inductance required. It will be of the order of nanohenries, right? Your capacitance is 47 PF and you want a resonant frequency at 50 megahertz, you calculate, it will be of the order of nanofarads, nanohenry, the inductance. And if you take simply a piece of wire of a length of about 5 centimeters, the self-inductance of that wire itself would be around that. Okay. Now, the only problem with this is the wire resistance, however, can be substantial enough to affect the quality factor value. In the sense, you are assuming that the inductor is totally ideal. It is not ideal. It itself has a series resistance. So that resistance will interfere with this resistance, and the value of Q that you will get may not correspond to the quality factor of the capacitance. So the quality of the inductance will influence. Whereas the standard inductance that you get is made of such a material which has very low series resistance and so on. But nevertheless, this is not very difficult to, this problem is not difficult to tide over, because we had diodes which were imported and whose quality factor was known to be more than 400. So all that we needed to do was you put an imported diode and you put a simple straight wire of 5 centimeter length here as an inductor, and then you do get a frequency of 50 megahertz, a resonant frequency. You find out what is the Q, and then you replace this particular diode which is imported, which is known to have a Q more than 400, with the diode that you have fabricated, and then you put it here and try to compare the Qs. So by this comparison approach and using a simple straight wire as a self-inductance, we can do this. So that is how, in fact, we solved it. You didn't have to wait for 2 months to actually measure the exact value of the quality factor. So these kind of situations arise often in engineering, where in the given situation with the available things, you have to solve the problem, right? And it is possible in many cases to solve it. This is what we are seeing repeatedly. I will just now end with another example related to this same problem of technology development. Now I will get into the structure. So how do you basically realize this silver bump on the semiconductor piece? Okay, it is done by electroplating. So I will just talk about one problem that is associated with this particular process of metallizing a semiconductor chip, and then see how it was solved. Okay, so practical semiconductor wafer, for those who do not know, I am just giving a quick review. It is basically a semiconductor wafer which contains many diodes. So ultimately, you want just one piece like this to encapsulate. But practically, a semiconductor wafer, if you see, it will be about, say, maybe a few inches diameter. Whereas this device will be a square of maybe 1 millimeter size, right? Cross section. I'm not talking about this cross section, but the section perpendicular to this particular slide, size of the diode. 1 mm by 1 mm, let's say, around that. So you will have hundreds of such devices made simultaneously on a semiconductor wafer. So you have to metallize all these devices parallelly, simultaneously. Okay, so what is the method of metallization? Now, it is plating, electroplating. All of us know about electroplating, even if we are not electrical engineers. In our school days, we have studied about electroplating. So all that you need is, you need an anode. Supposing I want to plate silver on this chips, right? I need a silver anode, and then I need an appropriate bath, and apply a voltage, pass a current. This current passes through these openings, and these regions are insulators, right? These are insulators. And then metal grows in this region. So this simple arrangement, basically the principle that we have to follow. Now, unfortunately, when this was tried, when you try to do this in practice, what happens is, this is practically what happened. So this shows a semiconductor wafer. Instead of getting the plating on these areas, these diodes or these junctions, there was a thick plating at the edge And there was a very, very thin, almost, no plating on these areas where we wanted to plate. In other words, that was the plating was here in these regions and not in these regions. So what is the reason? So again, to analyze this problem, you need to make a model of the situation. Okay. So what is the model of the situation? The model of the situation is, how is the current flowing? So current is flowing through this, and the current is flowing through this edge. Okay. And current is flowing through that edge also. It is not shown here, but that is basically how. And evidently, if this is what has happened in practice, it means that the amount of current flowing through the edge is much more than the amount of current flowing through this. Though that if I find out the area that is exposed here, I sum up all these areas, that area will turn out to be much more than this exposed area on the side, which is a very thin semiconductor wafer. But, and this is a crucial point, this is a PN junction which drops a certain voltage, whereas here there is no such junction. So what happens is, even though the area exposed, area of current flow is more, there is a voltage drop, series voltage drop here, which is absent in this lead. So therefore, in effect, the resistance of this path is much less than the resistance of these paths. And that is why most of the current is flowing like this. Okay, now how do we solve this? So one way is, of course, you can try to put some insulator, right, paint or something like that, some solution on the side, but did not seem to work so effectively, right? Because this is a very thin, right? And then it struck. So this is again an example of how to come out of a mental set. Okay, so it struck that actually, so this is a model. So again, the representation is important here, right? This equivalent circuit. This region is this resistance, and this particular junction is a diode here. Whereas for this, you only have the resistance, no diode in series. And this is why the effective resistance of this path is much less than resistances of each of this. So you just replace the DC by AC. Instead of using a DC source, you use an AC source. Now let's see what happens. And this particular change of the supply is motivated by the property of the diode or junction, that it allows current only in one direction. The other direction current is really very, very small, the bias. When this side is positive and this terminal is negative, the current will be negligible. The large current will flow only when this is positive and this negative. Whereas if you take this, there is no junction here. So this resistance, even though it is small, it will allow current in both directions. So in both half cycles of the voltage waveform. And as a result, if I average the average current in this path is 0, whereas the average current in these paths is non-zero value. So now you see, just by changing the power supply from DC to AC, I have ensured that actually there is an average positive current in these paths and average zero current in this path. So this actually worked. So here is the consequence of AC plating. You can see that there is no plating on the edge as it happened here. Okay, and there is plating only on these areas where we want it. So this again an example of a simple, but the critical point here is your mind, because our mind is used to using a DC supply for electroplating. Why? Because basically you want to plate, you have to pass current in one direction, right? So that is why there is a certain fixedness, functional fixedness, we can say here. Or we can even put this barrier in the category of mental set. That always positive, DC power supply is used for electroplating. Okay, so whereas if you come out of that, then you have found a very simple and elegant solution to the problem. Okay, so I think with this, I will stop because it is exactly an hour. So I had timed it like that, though it was suggested that I restrict myself to 40 minutes. So I will just summarize once more. What are the strategies of problem solving? This is just a minute I will take. because summary is very important after we discuss things. As teachers, we all know this. So reformulation of the problem, reduction of the problem to some other problem, representation of the situation or modeling is very, very important part. Divide and conquer, logical reasoning, trial and error, analogy. These are the strategies that are normally used to solve any problem, and these are discipline independent. That's the point. Okay, discipline independent. So our mind should get used to working in a discipline independent fashion for solving problems. And these are the barriers to problem solving. A mental set, that is a tendency to solve a problem using approaches that have worked in the past. So prior knowledge is a barrier. So this is very interesting, and a very interesting part of psychology, that unless you have knowledge, you cannot solve problems. But the knowledge also introduces a mental set. Okay, that you tend to use only those approaches which you have learned to solve problems. Okay, that is a mental set, a tendency that is there. And functional fixedness, that is using an object or a concept for a specific purpose for which you have been taught, and not for other things, right? So these are the two major barriers to solving problems. And finally, engineering is ultimate goal of engineering is product and processes aimed at practical ends. These should be safe, eco-friendly, efficient, economical, reliable, easy to fabricate. We didn't actually, my talk didn't focus on these aspects, but nevertheless, I want my audience to know this. And what does it require? It requires a reasonable knowledge of science, mathematics, logic, economics, ethics. So the problems that I discussed, you would have seen, for example, how to measure the Q of a capacitor, or how to plate the semiconductor chips. In both these cases, it didn't require deep knowledge, right? Elementary knowledge. These are school level knowledge, right? And ability to identify variables that can be ignored in a given situation based on hands-on experience and intuition. And very important, critical and creative thinking. This is the major thing, right? And also communication skills. How will you communicate your solutions to others? Okay, so with that, I will close my talk. This is a photograph of our campus, which has deers moving about. So if you have not visited our campus, I hope that this photograph will motivate you to come to our campus, right? And this is the one of the Indian words for thank you.
Thank you, Professor, for your interesting presentation. It was very interactive with those question and answers. Some was like really difficult questions to answer. Well, but this shows this mental set and things that you talked about, that sometimes we just focus on like one way to do it, and then we cannot do it like any other way. So we should actually like teach our students to like do different approaches, and like not like be like focused on like on one discipline. Well, thanks for this one. Usually we have time for questions. Well, maybe we can take like one or two questions. We're a little bit of over the time. If anybody would like to ask a question, please put it in the chat. I'll just wait for a few seconds. I think you have covered lots in your presentation with very good examples from your teaching experience. I like it how we talk about your students who broke computers and who couldn't solve those problems. And you had to explain that we can solve it in a different way, which is a very good example. Well, I think if we don't have any questions, what I will do next, I will just thank Professor Karmalkar again for his time and for very interesting presentation. I'm sure we can learn lots from his way of teaching, how we can engage students better in learning teaching process, so that they don't focus only on one discipline. And then I just want to thank you again, Professor. Thanks for your time, and thanks the audience for attending this seminar. We will run these seminars every month, so probably we'll do one maybe in January after the break or February. So we will let you know by email. Please attend the seminars, and we'll be very happy to see you. Thank you, everybody, and have a nice holidays.
Thank you. Thank you for the opportunity to speak.
If anybody wants to say something.
Thank you very much, Professor Karmalkar. Very, very interesting. I mean, as always, it was nice listening to you after some time. Thank you very much.
Thank you.
Thank you.
Thanks, everybody. I will just conclude the seminar.
Yeah.
Yeah.
Thank you, Ivan.
Yeah.
Thank you. Bye.
And see you next year. Have nice and safety holidays.
Oh yeah. Happy New Year to you. Happy Christmas to everyone. Happy Christmas. Happy New Year.
Happy Christmas. Happy New Year, everybody.
Yeah.
And have very nice holidays. See you next year.
Yeah. Sure. Ivan. Yeah. Bye.
Bye, everybody.